Hi, and welcome to the Advanced Algebra Tutor. In this course, we're going to continue where my other DVDs left off and continue on our path of algebra and pretty much covering most algebra that anyone would encounter, okay? So I struggled a little bit with what to call this class because I titled it Advanced Algebra, but I want you to know as we start off on this journey together that nothing in this class is really hard, okay? It has a title that sounds hard, Advanced Algebra, okay? But nothing is difficult if it's explained in the right way. So my goal is to teach you everything step by step so that no topic sounds tough or intimidating or hard. And we're going to do that by working example problems for every single topic here. Okay, so just stick with me step by step and you'll be able to do just fine. The other thing I want to say is that this class is kind of a little bit of a hodgepodge of things that I felt like people have requested over the years and that I felt like people should understand when going on and continuing their studies of algebra. Things in this course are covered either in an Algebra 3 class, sometimes there's a class called Algebra 3, depending on if you take that. Some of these topics are actually taught in Algebra 2, depending on the class that you take and the teacher that you have. And all of these things are covered in a college algebra class. So if you're taking college algebra, you're definitely going to need this DVD and also my other algebra DVDs to ace that class, and it's very comprehensive once we have those, okay? So let's just get started here. The title of this section, the first section here, is called Graphs of Functions, okay? In my previous DVDs, we talked about graphing lines, we talked about y equals mx plus b, and graphing a line, and on the left-hand side, it was always y equals something, mx plus b, or 3x plus 2, or y equals 5, or something. And what we were doing there was we were creating a table of x values and y values, and we were plotting them, and we were drawing lines mainly is what we were drawing. And now we're going to expand our envelope into the realm of functions, okay? So I want to dispel this myth with you right now. A function is very, very simple. A function is a fancy word that just means y equals something, okay? So instead of saying y equals 3x plus 2, you have a function that you define that equals 3x plus 2. It's just a new word for the same thing you already know. Okay, and we're going to see that right here. So let's just get started, and I'll write a definition on the board. I'm not going to write too many definitions in this class, but I'm going to do it here. A function, okay, a function, which is a term that you really need to know, and we're going to denote this function f of x. This is not f times x. Parentheses here does not mean multiplication. It's f of x, and I'll explain what that means in a minute. All this thing does is it takes an input, and the input is x. That's why it's f of x. It's taking an input. We call that x. And this is my terminology here, it spits out, I'm actually going to write this here, spits out another value, and we call that other value f of x. Okay, so this is exactly what it is. It's a function. I don't know why exactly they call it a function. I guess you could probably say that it performs some function on some values of x. And so it's kind of like this box, okay? A function is kind of like a box. Just imagine this empty box. You have no idea what's inside of it, but we label it f of x. We take values in, and these values are x. And by the way, you know, we have a lot of letters here. This is a value. These are just values. These are, you know, x could be 1, x could be 2, x could be 25, x could be 1.5, x could be 1.9, whatever. Any number you want, put it in this thing and into this box. And inside of here is some mathematical gears. We'll look at some functions and show you what they look like. But it's something that changes these input values and it dumps out some different output values. We call these values f of x. It means f, which is a function, has operated or has, you know, otherwise messed with these values of input x, and you get some new values out. So you might put 1 on the input here, and you might get 7 on the output. You might put 2 on the input here, and you might get, you know, 39 on the output, whatever. And f of x is just some mathematical equation that describes what the what happens to the input and transforms it into the output. So f of x, which we'll look at all day here, that is actually the mathematical beast that takes the input and changes it into the output. Now, this is no different than what you already know from my other DVDs and also introductory algebra. F of x, they just called it y. Okay, that's all. So when you were dealing with equations of lines, you had something like y is equal to 3x plus 2. Well, this is exactly the same thing as the function f of x is equal to 3x plus 2. You see, this is why I get frustrated with math, history, and textbooks, because they spend all of this time teaching you y equals 3x plus 2. You finally understand that you put a value of x in, and you get a value of y out, multiply times 3, add 2, you get a value of y, and you understand this finally. You understand that you put a value of x in, you get a value of y. And then one day you turn the page and they talk about functions, f of x. And the students think this has got to be something totally different, because my goodness, why would they put another section in the book if it was not the same thing? Well, it's exactly the same thing. This is no different. This is just taking a value of x in, which is all you were doing here. You're putting a value of x in, put a value of x in, it goes right into here, multiply and add, and the value f of x that you get out is just the same thing as y. It's just a new label. It's just that when you start to get up higher in algebra, they like to call it a function so that it's kind of more directly kind of describes what's happening. The function operates on the variable x and returns something else. You just call it f of x because it's operating on x. So this is no different than what you've seen. A function is just a box. It takes some numbers in, changes them, multiplies, divide, you might take square root, you might do some other stuff in here, and the values you get on the output are just your values of y that you used to deal with. We just call them values of f of x because we're talking about the fact that it is a function, okay? Now, look at our definition. A function f of x takes an input x and it spits out another value, and we call it f of x, and this is the output here. That's what we're interested in. You can graph these just like you can graph, back when you learned how to graph y equals 3x plus 2. Okay? The way you would graph this is you would have your values of x here, and in the other DVD course and also in your introductory textbook, we would put y up here. And I would show you, look, this is a coordinate system. You have values of x that go this way, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever. And you have values of y that go this way, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever. And you also have your negative values of y, and you also have your negative values of x, and they go on forever and ever. And I would tell you that, and you would nod your head and say, well, okay, great. And then we talk about what we can graph here, okay? There is no difference from what you have already learned in talking about these functions, okay? Instead of putting y up here in this axis, I'm just going to put f of x, okay? That's all we're doing. Because don't forget, f of x is just a function. You stick some number in there, and you get another number back. It's the same thing y was doing for you. It's just a different label. So this axis here is called the x-axis, and this axis is called the f of x axis, which is what you would graph there. And so when you put x is equal to 0 in, you might get 0, and you might get a graph. You could draw a graph. It might look like something like this. Okay? As x increases over here, f of x might get higher, and then after a certain point, f of x comes down as you start putting higher and higher values of x in. So you see, up until now, we've talked mostly about lines, these straight lines, but in general, a function can be very complicated. It can have square roots, it can have squares, it can have lots of different things in there to make this graph look really crazy in some cases. But it's very easy. You can plot them, and you can do that, and we'll do that together. Okay, now a very important thing about functions that they're going to ask you to do right away, one of the first questions they'll ask you on your test, is something called the vertical line test for functions. Okay, so it's something that you need to know. It's very, very easy though, so it's not going to give you any problems at all. Let me write it down here real quick. The vertical line test for functions. Okay? What this really says, is that for each input x to the function, there is only one output, f of x. Okay, that's what you would say in words. Okay, this is the vertical line test. What you would say in words is that this function f of x, you're going to put numbers in and you're going to get numbers out. And what it's saying is, for every number that you put in, there is only one output, f of x. So let me show you what I mean. A picture is worth 1,000 words here. Okay, this is going to be demonstrated like this. This is our coordinate system here. This is x. We've talked about this. This is just f of x. So this is the output. Okay. Now let's say the graph that I have here is just a line. It goes like this. It goes on this way and this way forever and ever. And I don't even want you to care about what the actual function is that describes the line, but this is what it looks like when you plot it. You have a input x here and a corresponding f of x there that you would plot. Okay. Okay. So what this is saying is, now notice, for every value of x that I go up here in x, I've only got one value of f of x. Even if I go down, for every value I go down here to negative x, I've got a corresponding value for f of x. Okay? So this is a function by definition. What you're doing is you're defining a function. A function can only have one input, one output for every input. So an easy way to determine if a graph is a function or not is to do what we call the vertical line test. All you do is you draw your pencil up and down vertically. That's why it's called the vertical line test. And at any point, if it only crosses the graph at one spot, okay, then it's a function because there's only one value there. If there's another one, if you draw another line, it only crosses in one place. You draw another one, it only crosses in one place. You draw another vertical line, one place. So any vertical line that you draw should only cross in one spot, and if that's true, this is a function, and that's why it's called the vertical line test for functions. If you draw these vertical lines and they only cross in one spot, you have a function on your hands. Okay. Now let me show you what is not a function, because that's pretty important, and I think that'll clear things up just a little bit here. Okay. This is not a function. Let's say here's your graph here. Okay. And this is x, and this is f of x, okay, just like we would expect. Let's say you had a graph that looks like this, okay? And the question was, is that a function, okay? And what you should do anytime they ask you that is you just go straight to your vertical line test for functions. What you need to do is you draw a vertical line and you see how many times it crosses. Well, it crossed right here and it crossed right here, so it crossed 2 times, so this is not a function. Okay? So make no mistake about it, you do have a graph of something here. You have graphed an equation of some kind, but what I'm trying to tell you is there's a very specific definition for the term function, and that definition says that for every input x, there should be only one output, f of x. Now look right here. At x is equal to negative, whatever this is, negative 2, there is a value of f of x up here at positive, whatever it is, 4, and there's also another value at negative 4, whatever. So at this value of x, there's actually 2 values of f of x. Now contrast that to this, where every value of x only has one dot or one point on this function. Here at this value, there's actually 2 corresponding values on the output, f of x. So there's no unique output. There's 2 outputs instead of only one, which is what the definition says. You can draw lots of vertical lines here, and you'll see that each one crosses in more than one place. So it only takes one. It only takes one violation of one vertical line for you to find, and if you find one of those vertical lines crosses in 2 spots, then this is violated, because it says for each input x, which is this line here, there is only one output, f of x. You found a contradiction here in lots of different places, so that is not a function. Okay, so let's just get a little bit of practice with it. Let's say that, draw these a little bit smaller. Let's say we have something that looks like this, okay? And again, this is x and this is f of x, okay? Is that a function, okay? Well, all you need to do is try your vertical line test. You just go back and you start drawing lines, okay? Well, I draw a line, only crosses one spot, only crosses one spot, only crosses one spot. It looks like you might start to cross twice up here, but this is a parabola. We'll talk about those later, but it actually continues climbing in such a way that you'll only cross it in one spot. So that is a function. Okay, that is a function. For every value of x, there's only one value of f of x. Okay? So if you can draw your line vertically and it only goes through one spot, you have a function on your hands. Okay? What if you have, here's x and here's f of x. Okay, what if you have the almighty circle? Okay? Let's say you have a circle. Okay? Certainly you can graph a circle. Okay? You know, it has a center and a radius and all of that. And the question is this a function or not? And all you have to do is take your pencil and go through, and you'll see right away that at this value there's two corresponding values of f of x. You can draw lots of these things, and almost every, well actually every single place that you draw it, for a value of x you're going to have two values of f of x. So this is not a function. Okay, so that's the vertical line test. I think you understand the point. All you have to do is draw your vertical line, and if it crosses the function in one place for every corresponding value of x, you got a function on your hands. If it crosses in two places or more, then you do not have a function. You do have a graph, you do have a relation, you have something that you can graph on your paper, but it is not a function. That is a specific definition of a function you need to know, and I guarantee you they will ask it on your test and on your homework. Okay, now the next thing we're going to work on is actually practicing how to graph a function. Okay, it's very simple. You have inputs and you have outputs, and those are your x, y points, or your x and f of x points, and you can put them on your graph, you draw your little dots, and you graph your function. It's very simple. Okay, so we're just going to get some practice with this. So if you had to graph a function, we're going to get our first taste of a real function here. F of x, let's say that this this function was x squared minus 2, and you wanted to graph this. Okay, I want to just tell you one more time, it's no different than if this had said y is equal to x squared minus 2. You make a table, you have inputs called x, and this is your function that's operating on that, and you're returning an output, we call it f of x. In other words, here I've drawn just a few values, -2 to +2, and I've plotted them. But I could plot, you know, this parabola goes on and on forever. I could just put as big of a value of x in as I want. I could go on to infinity in x. There's nothing to stop me from doing that. So I could go on to positive infinity for x, negative infinity for x, and that would be perfectly legal. There's nothing in there, in this formula, in this equation, that's going to give me problems doing that. You know, some functions you run into imaginary numbers, you run into other problems, but this one I can put -30 million in here and I can calculate an answer and it's fine. So for this problem, the domain of this function, okay, which is what you'll be asked a lot of times, is -infinity to +infinity. Okay? Now the parentheses here mean that it's not inclusive, which just means that, you know, it's -infinity to +infinity. The parentheses mean I can't actually use -infinity as a real endpoint because you can never get to infinity. So I think you'll see what I mean when I do the next part with the range, and you'll see what I'm talking about here. But the parentheses means it's not inclusive. So it's -infinity to infinity, but not inclusive of the endpoints, because -infinity you can't ever actually get to, so you can't really say that you include that as one of your endpoints. What it's really saying here is the domain of this function is everything, all possible values of x. Okay? And the range, which is always the legal values of f of x, okay? Well, we just plotted this thing here. You can kind of tell that it bottoms out down here, but it goes on up to infinity. I mean, if I keep putting numbers in, it'll get bigger and bigger and go up to infinity. But it bottoms up down here. It bottoms up down here, out down here. So for the y values, or for the f of x values, the lowest value here is -2, and the highest value that it can get to is +infinity. Okay, so notice here, what this is saying is these are the legal values of f of x. If I plot the whole function, what's the lowest value it can have? That's -2, we've just shown you that. And the highest value it can have is +infinity because it goes on forever. Now notice I put a square bracket here instead of a parentheses. This is what I was telling you before. This means that this function's range is -2 to infinity, inclusive of -2, because the actual function actually does go through -2. So the legal values of f of x that come out of this thing go from -2, including -2, because it actually goes through there, all the way to +infinity, but the parentheses are around the infinities because you can't ever actually get to infinity, so you have to put parentheses around that. But the big picture even more than these parentheses and brackets things, is just for you to know that the domain just means what are the legal values of x, what can I plug into this thing legally, and what are the legal values that I get back from f of x. That is called the range. Okay? Let's go ahead and work another problem, and we'll see this time and again, and so you'll get some practice with it. Okay? What if your function is f of x is equal to x cubed? Okay? And we want to graph that. Okay? So we do the same thing. We set up a table, x and f of x equals x cubed. And we want to plot this. So I'm going to choose the same points as before because those seem to work out from last time. -2, -1, 0, 1, and 2. Okay? And I'm plugging these values of x into my function, which is x cubed. So I'm going to have, for the first one, -2 cubed, which is -2 times -2 times -2. So I'm going to have -8. You should convince yourself of that. Negative times negative gives me positive, times another negative gives me negative, and 2 times 2 times 2 does give me 8, so it's -8. Then, for the next one, I have -1 cubed, which is, you should convince yourself, -1, because 1 times 1 times 1 does give me 1, and negative times negative times negative gives you negative. Okay? And then if you put 0 cubed, you get obviously 0, 0 times 0 times 0, and then 1 cubed, 1 times 1 times 1 is 1, and then 2 cubed is 2 times 2 times 2, which is +8. So you see you've got some nice symmetry going on here. What would it look like if you were to graph it? Okay? If you were to graph it, then you would have x over here, and you would have f of x up here. These are the values of x, and those are the corresponding values of f of x. Okay? And what I'm going to do is I'm going to say, okay, I have 1 and 2 and -1 and -2. Okay? And over here, because I know I'm going ±8, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8. This is 8. -1, 2, 3, 4, 5, 6, 7, 8. This is -8. So I'm just labeling a couple of them here to keep the board kind of clean. Okay? So if I want to plot them, then -2, -8. So I go to -2, -8. This is the first point way down here. Okay? Next point is -1, -1. -1, go down a little bit for -1. Next one is 0, 0. It's going to be right here in the middle. 0 for x, 0 for f of x. The next one is 1, 1. So I go over to 1 and then up to 1 up here. Okay? And then this one is going to be 2, 8. So I go over to 2 for x and up to 8 up here. Okay? And it may not be totally clear what the shape of this is going to look like, but if you were to put more points, it would show you that it's going to look like this. Okay? You have this nice curvy S. Okay? So anything with a cube is going to have some general shape that looks like this. The square term, you know, the functions that have x squared in them have that general shape of looking like a parabola like this. Okay? And the functions with cubes in them have this general shape of this kind of sideways S here. Okay? So that is the graph of the function. Now let's ask yourself, what is the domain? Okay? What values of x am I allowed to put into this? Well, I think you probably see that you can put any value of x into this. There's no restriction. I could put -20 million. I could put +10,000. So the domain is -infinity to +infinity. That's exactly how you would write it down. You use parentheses here because they're really not inclusive of infinity because you can't ever get to infinity, but you see the big picture there. And the range is what are the legal values that are pumped out of this function. And you can see by the way the graph goes on down forever and ever and up forever and ever, okay, that it's going to have the same thing. It's going to be -infinity to +infinity, okay? Because it can go on down to -infinity here and it can go on up to -infinity here. So the domain and range is really all numbers, -infinity to infinity, and negative infinity to infinity here. And you can see that it definitely is a function, because if you look at the vertical line test, everywhere you slice it, you only go through one point. So this is definitely a function, just like the last problem was definitely a function. Okay, the next problem is, let's say you had a function like f of x is equal to square root of x plus 1. Okay, what would that look like, and how would we plot it, and what's its domain and what's its range? So we do the same thing we did before. We create a column of x and f of x, and we just give it a shot. Now let's just pick these numbers, and you'll see why we picked them in a second. Negative 2, negative 1, 0, 1, 2, 3, and let's say 4. Okay, and f of x, we're just going to write it for reference as square root of x plus 1. Okay, now if we put negative 2 in here, we're going to have negative 2 taking the square root of that plus 1. Now you may or may not know this, but square root of a negative number is really what we call an imaginary number, and so for purposes of this graph, it's really not defined. So we put undefined here. It is an imaginary number, and if you know what those are, that's great. We'll talk about them later. But for the purposes of trying to plot it, it just doesn't exist. Okay? Same thing here. If you put negative 1 in plus 1, you got the same thing. You can't calculate that because you have a negative 1 there, and you're going to get an imaginary number. Now, when we try to put in 0, what we get is square root of 0 is 0. Plus 1 just gives us 1. So we can get an answer there finally. Let's move on to 1. Square root of 1 plus 1 is equal to, square root of 1 is 1 plus 1 is equal to 2. Okay, so we can get an answer there. Moving on to here, square root of 2 plus 1 is equal to, the square root of 2 is roughly 1.4 plus 1 is roughly 2.4. Okay. Putting this one in, square root of 3 plus 1 is equal to, the square root of 3 is roughly equal to 1.7 plus 1 is equal to 2.7, so we're getting some numbers here. And then the square root of 4 plus 1, the square root of 4, I think you probably know, is 2, because 2 times 2 is 4, plus 1. Okay, now when we put 4 into this function, the square root of 4 is 2, and 2 plus 1 is 3. Now what we want to do over here is we want to go ahead and plot it, okay? And so we have our x values laid out, and we have our y values, or our f of x is what we call them, values. And if we look at negative 2 and negative 1 for x, they're both undefined, so we really can't plot anything, so we just leave that blank, okay? We start at 0, and 0 is, has a corresponding value of f of x of 1, so we put a dot right there, okay? If we look at a value of x is equal to 1, f of x is equal to 2, so we move right up there, up to 2. And then when x is equal to 2, f of x is 2.4. So here's 2 and here's 3, so 2.4 will be right around there. Okay? Now at a value of 3 for x, f of x is 2.7, which is a little bit higher. And at a value of 4, f of x is exactly equal to 3, which is right up here. Okay? So you may or may not see the pattern here, okay? But what this is trying to tell you is that this graph, or this function, starts off here and it kind of bends over and goes on kind of forever like this, okay? So that is what the function looks like, and the question is for you, is it a function? Well, you do the vertical line test, you start cutting like this. I only see one point that I'm cutting through no matter where I go, so it is a function. Yes, it is, okay? What is its domain? Okay, what is its domain? What values of x is legal to put into this thing? Well, we can see that we can start at x is equal to 0 and go on and on forever to the right, but anything to the left gives us undefined answer, so the domain, the legal values of x that you can put into this thing just isn't going to go any farther to the left, because you don't get a valid number on the answer there. So the domain is going to be from 0 to infinity, because you'll see that you can't go any farther to the left for x than 0. And you have a solid bracket here, meaning that 0 is inclusive. So 0 is part of the domain. And x equals infinity, you can go on and on to the right. And the range, what is the range? what values of f of x are legal? Well, you have nothing less than f of x is equal to 1, okay? So you have a range of 1, 2, and how far up can it go? Well, you see it bends over, but it still very so slightly approaches infinity, so it's 1 comma infinity. So the f of x value, the y value, so to speak, the minimum that it gets is 1, and so that's why you put it here. And even though it bends over, you see, if I go far enough over in x, it'll still get higher and higher and higher, ever so slightly. So it does approach infinity, just very slowly, and that's why we put it like that. Okay? So these problems are really all the same after you do a few of them, and you just need to make your table of x and f of x, plot them, and you look at that and you figure out what your domain and range actually is. We'll do one more, and we'll say, what if your function is f of x is equal to 2 times the absolute value of x? Okay? Well, what we would do is we would put a table of x, and then f of x is equal to 2 times the absolute value of x. That's what we would do. And x, we're going to choose some values, -2, -1, 0, 1, 2. Those are going to be my favorite values, and I'm going to put them into here. Putting -2 in is going to be 2 times the absolute value of -2, which is going to be equal to, and don't forget what the absolute value is. It just means you put a negative or a positive in here, and you always get a positive, the positive number out. So if you put -2 in the absolute value, you get +2 out. If you put -57 in, you get +57 out. If you put +20 in, you get +20 out. So basically, it just strips the sign off, is all the absolute value really does. So, since all this is going to do is strip the sign off, it's going to give you +2, then 2 times 2 gives you +4. Okay? For the next value, 2 times absolute value of -1, it's going to strip this sign off, so it's going to be +1 times 2 is going to give you 2. 0 goes in, 2 times absolute value of 0. Well, the absolute value doesn't do anything at all to 0, so it's still 2 times 0, which gives you 0. And putting 1 in, 2 times the absolute value of 1 is going to be 2 times 1, which gives you 2. And then for the final one, putting 2 in times the absolute value of 2 is just going to be 4, because absolute value just keeps the positive value here. So you see I have some nice symmetry going on there for your f of x value. So what we want to do next is let's go ahead and plot that and just see what it looks like. Okay, we have x and we have f of x. Okay, and what we want to do is we want to go ahead and put our values in. Here's 1 and 2 and -1 and -2. Okay. And on the y values, we're going to go ahead and go 1, 2, 3, 4, -1, 2, 3, 4. Okay? And we want to plot. So for -2 for x, which is right here, -2, the corresponding value of f of x is 4, +4, which is right up here. Okay? For x is equal to -1, the corresponding value is +2, which is right here. For x is equal to 0, f of x is equal to 0. And for x is equal to 1, f of x is equal to +2. And for x is equal to 2, f of x is equal to +4. So, what you will see in general for any function that has an absolute value sign is you're going to kind of see this kind of upside down triangle looking thing. Okay? So what the absolute value does is it takes all of your negative values and it strips the sign off of them, so you're going to get positive values here, and that's why you get this sharp point in the middle, because all of these negatives are getting turned into positives, and so it just kind of bounces like this. Okay? So what is the domain of this? What is the domain of this function? Okay? What are the legal values of x you can put in here? Well, you can put any value of x into there. You can put -20 billion, you could put +30 million. So it's going to be -infinity to +infinity. Okay? What is the range? Okay? What values of f of x come out of this thing legally? Well, you see nothing ever goes negative, because that's what absolute value does. It never goes down here. Okay? But it does go on up to +infinity. So what you'll say is it's 0, +infinity. It's 0 on the lowest for y, That's as low as it gets for 0, and it's inclusive, and that's what this bracket means, because I'm including 0, because it actually does go through 0. It goes on up to infinity, but you have to use your parentheses for that because you can't ever actually get to infinity. So this section has dealt with functions, the definition of a function, what is a function, the vertical line test, and also plotting some functions to see what they look like so you get some experience, and also trying to define their domain and range, which are just big fancy words that mean what legal values of x does this function have when you plot it, and what legal values of y does it have when you plot it. And so I think with some practice this will become clear and you'll be able to tackle this on your test.